In section 12.5, we begin to look at what is known as the collision theory that's going to give us an explanation for how the rate constant depends on the temperature at which we are doing our reaction. So we know that for a reaction to occur, that the reactants must collide, and that anything that causes an increase in collisions between the reactant particles will increase the rate. And it's for this reason that increasing the concentration tends to increase the reaction rate. So you can see that in this example here, by doubling the concentration of that molecule there, I've doubled the likelihood that there will be a collision with the other reactant. Similarly, increasing the temperature will increase the average speed of the particles and the likelihood of them colliding. So if a collection of particles is moving around randomly, there's going to be more collisions if those particles are moving quicker. And so as we increase the temperature of our reactants, you can see that the average speed of our particles increases, and therefore our reaction will go quicker because it's just more likely that those reactant particles are going to bang into one another. And we know this from experience that if you want to dissolve a solid in a liquid, if you warm the liquid up, it'll go quicker. And the general rule of thumb is that you'll double the rate for every 10 degrees Celsius increase in the temperature. That's the kind of the rule of thumb. It doesn't hold perfectly, but that's what you can expect. So if we go from room temperature doing our reaction all the way up to 100 degrees Celsius, you can see that we're going to double the rate, like 8 times. So that's going to be a significant impact on the rate of a chemical reaction. And something interesting is that when the reactants collide, they must do so with enough energy to break the bonds in reactants and allow new bonds to form that are present in the products. So when I look at this reaction between N2 and O2, this reaction is notoriously slow. It only takes place at very high temperatures. So there's plenty of N2 and O2 that are in the atmosphere and they don't undergo this reaction. But at the high temperatures that are present in your the engine in your car, this reaction does occur to a small extent. And you can see why, because I've got to break a whole bunch of triple bonds and a whole bunch of double bonds, and that means moving an awful lot of electrons around, and those bonds are quite strong. And then in return, all I get is 2 triple bonds back. So I have to move a lot of electrons around in order to form the products and break the bonds that are in the reactants. So the minimum energy that the reactants must have in order for the reaction to occur is called the activation energy. We talked about this earlier. And so the reactants have to get over this sort of hump on their pathway towards the products. And if I increase the temperature of my reactants, my activation energy doesn't change. I increase the proportion of reactants that have energy greater than the activation energy, so my reaction will go faster. Now, there's a guy called Arrhenius, who I believe was Swedish. He figured out the exact dependence of the rate constant on temperature, and he found that there was an exponential dependence. So the Arrhenius equation reads that the rate constant is equal to the frequency factor, that's what A is, multiplied by e to the power of the negative of the activation energy divided by the product of the ideal gas constant multiplied by the temperature. And we have to remember here, whenever we're using the ideal gas constant in equations related to energy, that we've got to use the value of 8.314 joules per mole per degree Kelvin. So what is this term A that appears at the front of the Arrhenius equation? Well, A is referred to as the frequency factor, and it takes into account that not all collisions are effective even if they do have the required activation energy. So here's a reaction that occurs in the atmosphere between ozone and nitrogen monoxide. It forms O2 and NO2. So here are our two reactants. Here's our molecule of ozone and here's our molecule of NO. And the purple end of the molecule is the nitrogen end. What we want to form is oxygen, nitrogen, oxygen. So that means that the nitrogen of the NO has to collide with the O3. If we have it the other way around, where the oxygen of the NO collides with the O3, you can see that there's no possible way, no matter how hard they hit, that we can go on and form the products. So when the guys collide oxygen ends together, we get an ineffective collision. Even if we have the activation energy, and it won't form products. We have to have the nitrogen end of the NO colliding with the O3 in order to form the product. So the frequency factor takes that into account. It's kind of, going to be determined by how precise an orientation that we need in order to have an effective reaction, or an effective collision, I should say. When the reactants collide with the correct orientation and enough energy greater than the activation energy, then we might go on to form the product. So what will happen is they'll come together. It's an effective collision, which means it has enough energy and it has the correct orientation. And then what are we going to start doing? We're going to start seeing bond breaking and bond forming occurring. And when we're exactly sort of like halfway between our reactants and products, we have what is referred to as the activated complex. So in the activated complex, we've kind of begun to break the old bonds and we've begun to form the new bonds. And we're, exactly halfway between our reactants and our products. The activated complex is an energy transition state. So we're kind of like right at the balance point between our reactants and products, and it is often referred to as the transition state. So another term that you'll see people talking about when they are really referring to the activated complex is called the transition state. You'll hear a lot of talk of that. Okay. So what we're going to look at now is what happens when we look at the forward and the reverse reaction side by side. So here's the reaction that we're interested in. NO plus O3 gives NO2 and O2. So we've got our reactants over here and we've got our products over here. And in this reaction, there's a loss of energy. So that's telling me that it's exothermic. Okay, so reactants here, if they can overcome the activation energy barrier, they can go on and form products, provided the collisions have the correct orientation. Now let's just mirror this curve around the transition state. So what we've got now is a curve over here where what was the products are now the reactants, and what were the reactants are now the products. And so what you see here for this reverse reaction is the activation energy is a lot higher. So what does this mean? It means that the reaction is pretty quick in the forward direction and very slow in the reverse direction. So the reaction favors the forward direction. Now, this form of the Arrhenius equation is okay, we use it occasionally, but it's interesting to look at it in other ways. And one of the things that we can do is we can turn it into what we call the linear form of the Arrhenius equation. And what we're going to do is just take natural logarithms of both sides of this equation. And so I've done that here. And then we can see in here we have, we're going to apply our log rule for multiplication that says that log of A plus log of B is equal to log of AB. And I'm going to use that to separate out the components of this term over here. And so now I can write log K equals log of A plus log of E to the minus EA on RT. Now, the natural logarithm is just the inverse function of the exponential function. So basically that just eliminates that E there, and that gets me down to here. And I'm just going to kind of reorganize the terms. I'm not changing anything at this point. I'm just kind of writing it in a sort of like more meaningful manner. And this is the linear form of the Arrhenius equation that we'll frequently use. And it says that log K is equal to minus EA on R, multiplied by 1 on t plus log of the frequency factor. And so what you see is that we have an equation of the form y equals mx plus b, where y is log k, x is 1 on t, the slope is minus EA on r, and the intercept is the natural logarithm of the frequency factor. So what this is really saying is, if you make a plot of log k against 1 on t, you'll get a straight line. The slope will be minus EA on r, and the intercept will be the natural logarithm of the frequency factor. So a common way of determining the frequency factor and the activation energy is to perform a reaction at a number of temperatures, determine the rate constant at those temperatures, and then plot log k against 1 on t, get the slope, get the intercept, and you have the activation energy and the frequency factor. So we'll just have a look at this now. It says the following data was collected for the decomposition of CLO, and it gives you a series of rate constants, and it gives you a series of temperatures. And we can see that as the temperature goes up, the rate constant gets bigger. And the question asks, what is the activation energy? So our strategy is going to be to plot log of k against 1 on t. It'll give a straight line with a negative slope. The intercept will be log a, which we're not particularly interested in, and the slope will be minus EA on r. So here we are. I've just extended, so I've just taken the one, I've extended my temperature column out. It has to become 1 on t now, and then I extended my k column out to become log on k, and now I'm going to do log k against 1 on t. So there we are, and then I just pick the first point and the last point, and I'm calculating the slope. Now you don't need to make the graph. Obviously, you can calculate the slope without the graph, and if you're really adept and you watch that little video that I posted, you know that you'll be able to do this in a stat table and apply a linear regression and have your calculator do this for you. So I'm just doing it here. I calculated the slope of this line. So it's going to be the my first point minus, and I did the second to last point, divided by the 1 on t for that first point minus 1 on t for that second to last point. And then that gives me the slope. You want to keep in mind that the slope is minus EA on r, so I've got to multiply both sides by minus 1 and r in order to get the EA. So that's what I'm doing here. There's my slope multiplied by minus 1 multiplied by r. And there's my activation energy, and that's a pretty typical activation energy. They're normally like, a few kilojoules per mole up to maybe perhaps a few hundred kilojoules per mole. Another way that we can express the Arrhenius equation is in the 2-point form. So we're just going to consider a reaction that's been performed at two temperatures, T1 and T2. And we can write out the linear form of the Arrhenius equation at T1, and then the linear form of the Arrhenius equation at T2. And they'll have the same activation energy and frequency factors at both of those temperatures. Those things are not dependent on the temperature, but they'll have different rate constants. And at the higher temperature, the rate constant will be bigger. So now what I'm going to do is subtract both these equations from each other, and then I'm going to collect like terms. So log k1 minus log k2, I'm just going to use my little log rule there. ln of a minus ln of b is equal to ln of a on b. So that's what I've done to the left-hand side there. And then you can see here that some of these things cancel out. And then, yeah, ultimately I'm left with this expression here when I collect the terms for that are multiplied by minus EA on R. So that's what I've got there. And now, so if I have two temperatures, the activation energy, you know, I can get the ratio of the rate constants. So what's important about this expression to realize is that it won't give you A. Okay, so, you know, it's kind of, it's of limited use, this 2-point form, but it definitely avoids calculating slopes and plotting graphs and things. Okay, so here's an example. It says the following data was collected for the decomposition of N2O5. We have a series of rate constants, we have a series of temperatures, and you can see as the temperature goes up, the rate constant gets bigger. This is a first order reaction because the rate constant has units of times to the minus 1. So it says what is the activation energy, and then it says what is the rate constant at 300K, and you can see that there's no value in the temperatures for 300K. So the first thing I'm going to do is I know that the activation energy is the negative of the slope of my log K on 1 on T plot multiplied by R. So I'm doing log of my first rate constant minus log of my last rate constant divided by 1 on my first temperature minus 1 on my last temperature. That gives me my slope. And then I multiplied that by R. Don't forget to take the minus. Activation energy is always going to be a positive number, so if you forget to take the minus, it works out in the end. And I got 101.6 kilojoules per mole, which is ballpark correct. So now, this is where we get to use the 2-point form of the Arrhenius equation. It says, what is the rate constant at 300K? So, what I'm going to do is use the 2-point form. So log of K1 on K2 is equal to minus EA on R. We just solved for EA, multiplied by 1 on T1 minus 1 on T2. So I have a couple of options here. I have all the numbers that I need to put into here. I could just use the solver to solve for the K that I'm interested in. So, you know, perhaps I let that be the K that I want to solve for, and then this would be 300K, and then K2 and T2 would be any of the values, any, you know, one value from that table up there. So I didn't do that here. I did old school algebra. So again, I just kind of split this down. Log K1 on log K2 is equal to log K1 minus log K2. So I've used that to my advantage here in getting this expression. And so now I just go ahead and solve for log K1, where K1 is the rate constant I'm interested in. See here how I had to put my EA in joules, or otherwise my units are going to be out, because R is in joules. So they have to be in joules. They have to both be in joules. So that's why there's the 10 to the 5 there. And then my temperatures are in Kelvin. And then I just picked the first one to be my T2. So as long as I keep that straight, looks good. Yeah. And then I got that value, and then to undo the logarithm, I take this value, I take the e to the power of that value, and that gives me my rate constant. And you know, the rate constant at 658 Kelvin was 2.1 by 10 to the 5, so I would be expecting a number that's a lot smaller. Remember that the rate constant exponentially depends on temperature, so it's probably going to be a lot less, and it is. So that's really it. It's still a first order process. That's why we have those units there of seconds to the minus 1. So that's using the, we use the linear form to get the activation energy, but then we use the 2-point form to get the value at a different temperature that we didn't have experimental data for.